In this video, we're going to be talking about what is GD&T. If you're studying mechanical engineering or working in the design or manufacturing world, you've probably at least heard of GD&T from the people around you. Regardless, you want to know more about GD&T. So let's get into our 11-minute discussion introducing you to GD&T so that hopefully you could know how well it could help you in your career. But before we discuss the basics of GD&T, be sure to like this video and subscribe to this channel to continue learning about engineering careers and how to be successful in them. Be sure to stick around to the end of the video to really learn the essentials. So let's look at some examples just that are kind of random on Google, and I think the biggest example that you'll find when you use GD&T and when it has a practical purpose is like if you're mounting a bracket or something that's being fastened into a fastener interface. And so in this case, we have this four fastener pattern and there are slots in here, so that helps us as well. But if we were to have a different pattern of wherever this is being mounted to, like for instance, a car chassis or somewhere on a car engine, and then we were to fasten the four bolts. The problem is that we have on an engineering drawing where the dimensions of these four holes and where they are with respect to each other. But in practice, when we manufacture this bracket, when we drill holes in here, it's not going to be perfect. We might have some really high-tech equipment for making sure the holes are spaced properly, but not going to be perfect. But the thing is that we have these engineering drawings. Let's find an example. And this is a bracket with holes in it as well. And so it specifies where the holes are, and this box with all these numbers and symbols in it tells us this is how far off the holes can be from each other or in their assigned position, and also the tolerance of the diameter of the hole itself. We'll get into what all this symbolism means in a minute, but that's the basic sort of how they assign the position of the holes and the size of the holes and how far off those could be to really make sure that this mates properly into wherever it's supposed to go. And so in this example, if we have our four holes over here, then whether or not it fits properly is going to depend in part on the tolerance of these holes themselves and also the position tolerance of the holes with respect to each other. So like for instance, if the holes were too far in, then the fasteners might not all go through properly. And so in the end, there would have to be some kind of inspection to make sure all four of these holes are within the required specifications that are listed in this equivalent right here, whatever would be this bracket's equivalent of all these symbols and stuff. So that's what we would look at. And so looking at some of these, so for instance, this means that the position tolerance, it's a diameter tolerance of 0.14. This M symbol means maximum material condition, which we'll get into in a bit, but it's a diameter position tolerance of 0.14 at maximum material condition, so meaning that the center of this hole can be 0.14 off from what's assigned on this drawing at maximum material condition. And then these two, A and C, these are datums. So in this case, datum A, it's basically like a reference surface or a reference point. And so it's assigning datum A as being the flat mounting surface in this case. So 0.14, it can't be that far off with respect to this flat surface on datum A. And then also with respect to datum C at maximum material condition, datum C looks like it's the center of this bore in the center. So that's what we would have for this, for instance. Let's start by going over some of the various tolerances that do exist. Well, like with all these symbols right here, like we looked at position tolerance. That's the symbol that we saw in that other drawing. So there's just a lot of these different symbols for dimensions, and showing what the tolerances are, or aka how far off they can be. So straightness, if you have like this edge, for instance, or more importantly, like the flatness would probably be a bigger thing. Like, so the flatness of this bracket, whether or not it's properly flushed up to whatever it's being mounted to. And so you would measure that by measuring the surface and if it has bumps on it and had the length of those bumps, how far off they really are from a straight surface. Because it's never going to be a perfectly straight surface, but the question just is it within the tolerances here? Like if we can go back to this, yeah, it looks like flatness tolerance in this case is 0.02. So that would mean that this surface can be within 0.02 inches, or whichever unit this is, probably inches. So 0.02 inch flatness tolerance on this flat mounting surface of the bracket. Let's see if this list had any other interesting ones. Circularity, I mean, that's another thing. Like in theory, they could have done that for these holes, but they're already assigning that through just the dimension tolerance of the hole, which is above there, saying that the hole here is 7.9 to 0 to 8.1. Okay, so it can be within, it can be anywhere from 7.9 inches to 8.1 inches. So that's what it assigns as the tolerable zone. So in theory, it could have been a circularity tolerance, but it was easier in that case to just put the size tolerance. And cylindricity is, it's the kind of thing where like some of these you're going to be using 90% of the time, especially like the position tolerance and the size tolerance and everything like that. Perpendicularity may come in as well. Let's see, did they put that one here at all? Not really, although they put a parallel, looks like, between these two lines, probably. Make sure that they are parallel within 0.06 with respect to datum A. Interesting. And then angularity, just to make sure that an angular dimension is within its tolerances. Concentricity would also be an interesting one in this case. Let's see if they use it, because it would be concentricity of this sort of outer bore with the entire thing, but it doesn't look like they use it because they probably achieved the same thing just with some other dimensions, mostly probably just with the position tolerance of this hole and the position tolerance of the mounting holes right here. And then symmetry. So yeah, that's the biggest stuff that's used in this case, which, yeah, most of it is going to be like, because you're making sure that parts fit together properly. And so most of it is going to be like, can you mount this part without there being interferences or issues, without having issues getting fasteners to fit properly? And let's also talk about maximum material condition, and that is pretty much exactly what it sounds like. So let's think about, for instance, these fastener holes, which can be between 7.9 and 8.1 inches in diameter. And so with that tolerance, whatever size in that range would give us the most material in the bracket is the maximum material condition, which that is pretty straightforward, but I will note it can be easy to slip into thinking the biggest hole is the one with maximum material condition, but actually the smallest hole is maximum material condition because we're talking maximum material in the bracket, if that makes sense. So in that case, the smaller the hole, the more material there is in the bracket. So 0.14 at maximum material condition, meaning that the smallest hole, or yeah, the smallest hole, meaning 7.9 inches on these hole sizes. And so that would mean that it can be a 0.14 position tolerance of the hole if the hole is 7.9 inches, basically. And the reason for that, because there's going to be kind of more leeway if it's not maximum material condition, because if you think about it, so if we're not at maximum material condition, so that would mean the hole is bigger, then there is more room for the fasteners to fit together. And so in those cases, you would be able to fit everything together if you're not quite at maximum material condition, but the position tolerance is off a bit more. And you just do some calculations to figure that out. And then in this case, note that C has an M value right next to it. Like, so C for maximum material condition, because that's datum C, meaning this hole right here. So maximum material condition with respect to datum C. So that would be datum C, like if this hole right here was the smallest it possibly could be.